Hello there, this is Toby. We're going to continue this series where we walk through the LLVM tutorial from LLVM.org. So we're in the middle of chapter 4 and we're about to add a JIT compiler. What the heck is a JIT compiler? Well, JIT stands for just in time. It means when you write a program, when you write a program, somebody wrote a program. Well, as you know, if you've seen my previous videos explaining the architecture, you're gonna parse the code, and then you're going to generate some code, generate some machine code. I merged two boxes into one here. You need some machine code and then send that machine code to your CPU. JIT is basically saying, well, I'm gonna do this step on the fly as needed, on an as needed basis, and I'm gonna have this program that is actually like interpreting your code. This program, and in particular, it makes sense for this toy language because this toy language is running within this REPL loop where you type some code into it, you type a little bit of code into it, it's gonna like compile it, and it's gonna generate some machine code. At this point, not yet, but at this point, it's gonna generate some so-called IR code. But this IR code, then, if we want to actually execute the program, we have to go through this generate process to give it. Oh, that looks horrible. This IR has to go to a box to convert it into machine code, which can then be fed into the CPU. And this process here, we're gonna do this just in time. Just in time, as needed. Okay, that's what is meant instead of ahead of time. Ahead of time is you give me the entire program, I'm gonna convert all of it to machine code and then execute it. Just in time means like, you have this program, fine, you just typed it in, or maybe it's even on disk. I'm not gonna compile it until I'm planning to execute it. When I want to execute it, I will compile it into machine code, and then I'll execute it right away. So that's what just in time is, and apparently LLVM has support for that. That sounds awesome. So in this section, we'll add JIT compiler support to our interpreter. The basic idea is that we want Kaleidoscope to have the user enter function bodies as they do now, but immediately evaluate top-level expressions that they type in. For example, if they type in 1 plus 2, we should evaluate it and print out 3. If they define a function, they should be able to call it from the command line. In order to do this, we first prepare the environment to create code for the current native target and declare and initialize the JIT. I love it that they called it the JIT. This is the JIT. This is done by calling some initialized native target functions and adding a global variable, the JIT, and initializing it in main. Okay. So, alright, there's a lot of mysterious stuff going on. I guess this code was already there in their example, although I didn't choose to use this precedence map here. So I just need to add these 3 lines, I believe, and also this line and also this line to initialize this static global variable called the JIT. There's this header file called a Kaleidoscope JIT. We'll get to that later, but you will need it if you're following along. Okay, I have the module the FPM and the JIT. And I need to add these 3 initialize function calls to the top of the main function. I'm not sure whether it should go before my other initialize function or after. I'll do it before. And then I need to initialize the JIT before I start the main loop. Okay, there, I have done it. I guess I'll delete this test code that I wrote for debugging the problem earlier on. Alright, now we also need to set up data layout for the JIT. So I'll go into this initialize module and pass manager function, which is right here. I need to add this line to say set the data layout. I don't know what that means. Okay. And then we need to create a I guess we already have this line. That's so this oh by the way, I think I covered this in the last video, but this actually needs to be legacy colon function pass manager instead of function pass manager. So this is a mistake in the tutorial. But their final code listing, if you just skip, instead of using these code snippets, you go to the final code listing, that code actually works. So if all fails, just fall back to the final code listing at the bottom of this chapter. The Kaleidoscope JIT class is a simple JIT built specifically for these tutorials. It's available inside the LLVM source code. So this file, I have dug it out of the LLVM source code, and I've copied it and put it in my project. The way you get hold of it is to just go to the source code page for LLVM. I think they have a GitHub. Pretty sure that they do. Yes. It's actually a mirror of code in another repository, I believe. And if you go, you can clone this entire directory. There's a lot of stuff in there, but if you don't want to clone it, I believe you can go into the examples directory. Maybe within LLVM. Yeah, yes. So LLVM project / LLVM / examples / kaleidoscope include. That's where Kaleidoscope JIT.h is, and you can go here and you can get this file. What's the best way to get this file? You can click on raw and then just copy this content from your web browser and paste it into a file with that same name. Although if you call it a different name, it's not a problem as long as you reference the name that you have for it. So I think that means I need to include that in the, I'll do it in the top. So reference Kaleidoscope with a K. Okay, so I include this header file here, which I have copied into my own project. And let's go back to the chapter. So in later chapters, so one thing, obviously one question I have at this point is, like, if you look at this source code for this so-called Kaleidoscope JIT, this code is, you know, there's 130 some lines. I mean, it's not a ton, but it's still, you know, you're gonna throw this much code at me without explanation. So I will probably want to go in this code and figure out what it's doing. But let's get through this chapter first before we do that. So in later chapters, we will look at how it works. Oh, okay. I will learn about it in later chapters then. That's fine. Great, thanks. And we'll extend it with new features. But for now, we will take it as given. Its API is very simple. Add module adds a LLVM IR module to the JIT, making its functions available for execution. Remove module removes a module, freeing any memory associated with that code in the module, and find symbol allows us to look up pointers to the compiled code. We can take this simple API and change our code that parses the top level expression to look like this. Okay. Let's go to the handle top level expression function. All right. So right now it is relatively simple. We're gonna add a whole bunch of stuff into it. It looks like. First, we're gonna use the JIT to get the module. Let me type this in by hand because I wanna internalize this better. Are we still gonna print out that we read a top level expression? I guess no. I'll leave it in there. Okay. So I'll say auto h equals the JIT add module capital M S standard move the module. Okay. So this is saying we're gonna we're actually going to move the ownership of the module to the JIT. So the JIT is responsible for the module. Interesting. We're gonna initialize module and pass manager. Oh, I think that means for every single expression, we're reinitializing the module and the pass manager. Interesting. JIT the module containing the anonymous expression, keeping a handle so we can free it later. Okay, then we're gonna search the JIT for the anon exper symbol. Do we even have that symbol? Underscore underscore anon exper. And then we're gonna assert exper symbol and function not found. Okay. Whoa, what is this? So the symbol's address and get the symbol's address and cast it to the right type. I guess the right, what even is that? Takes no arguments, returns a double, so we can call it as a native function. Oh. So it's saying whatever that address is pointing to a function that's going to return a double. Wow. Huh, okay, so That's interesting. So int pointer t. That probably just means, well, whatever the address gives you, it's really just a number which represents the address to some memory location. And we're going to interpret that as a pointer to a function that's going to return a double. So then we're able to call this function now using that. I see. And then calling this function will actually evaluate the code. That seems really cool. And then we're gonna delete the module, the JIT remove module H. Oh, we're gonna add a module just to execute this code, and then we're gonna remove it. It's a temporary, a transient module. Does this compile now? I want to try compiling this. Okay, let me try building this program. Oops, did not mean to do that. Does not build. Unknown type name Kaleidoscope JIT. Oh. I did include this header file. That's a thing that I did do. It did reference this though. Did I spell it wrong? I might have spelled it wrong. That's possible. 942. Right. I guess I did mean that. Maybe. Oh, because we define. Oh, I see. It's a namespace thing. So I want to use the namespace ORC because LLVM ORC is where this class was defined. Unexpected colon. Did you mean double colon? I probably meant double colon. I am not that good at C++, so that probably needs to be a double colon. Thanks for giving me that suggestion, huh? Is that Clang++ giving me that suggestion? Use of undeclared identifier. Initialize module and pass manager. So I guess I need to forward declare that sucker. Let's do that. Where do I forward declare these things? I'm just gonna do it near the top, like here. Okay, one more error. So this is saying cannot convert expected LLVM JIT target address, aka expected unsigned long to int pointer t, aka long, without a conversion operator. Okay. Wow. I didn't get this error though while compiling their version of the code. Maybe I should look at their version of the code. By the way, yeah, in general, so for you or anyone else who are, you know, in the business of building software, you're having to learn new things all the time, and you're gonna try to work through some tutorials, some learning material, and get stuck. There's no avoiding that. And this is why a troubleshooting skills is so important. The bug sandwich technique is a really useful technique for getting you out of this kind of situation. And yeah, if you're interested in learning more about that, again, go to debugschool.com for some of the videos that I made about debugging. Hopefully, I would like to help you improve your debugging skills in the long run. Okay. Anyway, so what I'm gonna do right now is try to maybe do a comparison between my code versus their code in the place where I have this thing here, this Xburst symbol thing. For me, it looks like this. I'm gonna look at their code, what it looks like over here. They have this thing called can't fail. I don't have that. Oh, really? What is can't fail? Yeah, okay. Can't fail is a function. They clearly added this just to get around this compiler error, I think. So I'm gonna slap a can't fail on mine. This is hilarious. It's like, oh shoot, compile error. What do I do? I'll just make a workaround to shut up the compiler. That's what I'll do. I'll call it can't fail so that it can't fail. I think that worked. Ooh, exciting. Segmentation fault. Okay. I wonder whether I should read on a little more before trying this or no. I think this is it, actually. Now I might need to debug the segmentation fault. Okay. If parsing, let me just read this paragraph and then I'm gonna decide whether I should go into the debugging session or leave that to the next episode. Okay, so if parsing and code gen succeeded, the next step is to add the module. Where's the, oh yeah, that step, containing tab level expression to the JIT. We do this by calling add module, which triggers code generation for all the functions in the module. Oh, I see. Code generation, that what they mean is it actually generates the machine code. That's what that means. And it returns a handle that can be used to remove the module from the JIT later. Once the module has been added to the JIT, it can no longer be modified. So we also open a new module to hold subsequent code. by calling initialize module and path manager. So so I guess you're doing that to, I don't really understand why these two sentences. Once the module that has been added to the JIT, it can no longer be modified. So I guess it's because we want that this added module to be temporary, this H module. We want it to be temporary, but once we add it, there's no way to remove it. So in order to have the temporariness, we kind of have to reinitialize the global module, which kind of deletes everything from it, doesn't it? Once we've added the module to the JIT, we need to get a pointer to the final generated code. We do this by calling the JIT find symbol method, excuse me, and finding the name of the top level expression function, which is underscore underscore anon underscore expr. Since we just added this function, we assert that the find module returned a result. Next, we get the in-memory address of the anon expression function by calling getAddress on the symbol. Recall that we compile top-level expressions into a self-contained LLVM function that takes no arguments and returns the computed double. Because the LLVM JIT compiler matches the native platform ABI, this means that you can just cast the result pointer to a function pointer of that type and call it directly. Let me try to process that sentence. Because the LLVM JIT compiler matches the native platform ABI. What is the native platform ABI? I don't really know. Okay, I'll have to research that later. But because of that, you can just call that function directly. This means there's no difference between JIT compiled code and native machine code that is statically linked into your application. And that is pretty rad. Final, which means it will be fast. That's really what they're trying to get at. It's like, it's fast, it's fast. Trust me, it's fast. Finally, since we don't support re-evaluation of top-level expressions, we remove the module from the JIT when we're done to free the associated memory. Recall, however, that the module we created a few lines earlier via initialize module and path manager is still open and waiting for new code to be added. With just these two changes, let's see how Kaleidoscope works now. It evaluates to 9. Well, basically, looks like it's basically working. Mine is not working though, so I'm thinking, should I try to debug this, or should I don't know. I'm gonna try a little bit to debug this actually. We got a segmentation fault, I believe. I guess there's a few ways to debug this. One is I can, again, look at theirs and see how theirs is different from mine. Another idea is I can do a step debugger, line by line, figure out at which step did things crap out. But it looks like it just initially, it already crapped out. And it could be that maybe we shouldn't call, yeah, they took this initialize module and path manager away from the main function, so maybe I should do that. Will that prevent it from sig faulting? Probably. Now the compile time is quite long. One pain point I feel like of developing code in C++ is the compile time, and that's a sentiment I get that I felt from C++ developers, is that it's a really pain for them to have to wait for the compile to finish. So that's yeah, okay. So I'm gonna do 1 + 1 semicolon 6. Dang it. Okay. So I'm gonna compare my initialize module and pass manager to theirs. Let's do a split screen. Oh, actually they did it down here after the JIT. Okay, maybe that's what I should do, but I'm still gonna do this comparison. What is this stuff here? Okay, that's probably coming later. I want to read their initialize module and pass manager function. See whether there are differences between that one and mine. Looks the same. Okay, let me rebuild it and hope that fixed the problem. It worked, or it compiled. 1 + 1. Oh! It was close. Assertion failed. Expert symbol not found. Okay. We can work with that. We generated the IR code, but now is this assertion, which I do remember writing that assertion. That assertion failed. Okay, and that assertion, let's find it. Let me compare it with their code. Okay. It looks the same as their code. A non-expr, a non-expr. And we're asserting the expr symbol exists. I guess. What is the assertion for again? We assert that find symbol returned a result. I don't detect a difference. Is there some other thing you have to do in order for this to work? Did we call this a non? Oh. This is the name they named that outermost function. I had a feeling that's what it was, but they never explicitly told me that. Maybe they did and I missed it. That could be. But anyway, oh, I accidentally closed out my terminal again. Okay. LLVM first link. Okay, let me try to build this again. Okay, compile. That was actually faster than last time. Quite a bit faster. 1 + 1, semicolon. It evaluated to 2. Okay. the compilation is working. We have machine code and we have a JIT and it works. That's beautiful. I can do more complicated stuff. Maybe I can. Let me try to define a function. Maybe the function is called add, and we're just gonna add x and y. Okay, and now let's do add 4 and 5 together. Evaluate to 9. Oh, that's freaking awesome. Beautiful. Okay, so I'm gonna stop this episode here. In the next episode, we'll keep going and hopefully finish chapter 4. See you on the other side.